This is the 10th section of the integration chapter, and this is solving differential equations. Now, a differential equation is where we have dy dx equals something, and we want to work out what y is. Yeah, now that will involve integration, and that will involve when you work this out, you'll work out and you'll have a plus c here when you integrate. Using the function notation, that would be if you've got f dash of x equals something, and again if you integrate it, then you will end up with f of x equals something. Now you know when you integrate we have this constant of integration. Now when you solve an differential equation, if your solution is written in the form y equals, or f of x equals something plus c, okay, we call this the general solution. The general solution. If we now work out what c is, okay, so if we find c, and to find c you're going to need some values of x and y to substitute into the general solution. So they may be what we call initial conditions. So for example, it might be when x equals 0, y equals something. So that's going to allow you to work out what c is. And then when you find c, obviously you'll just end up with y equals something. There'll be no plus c on the end, it'll be plus a number. This is what we call the particular solution. So we have a general solution when we have plus c. When we work out that what c is, we have what we call the particular solution. Don't like the look of that r. There we go, that's better. Now, how can we solve differential equations? Well, the type we're going to get, we're going to have to use what we call separation of variables. Okay, so separation of variables. Now what does that mean? That basically means that you're going to have maybe something like this. Let's say we had x plus 6 equals 7y dy dx, and we want to solve that. Do you notice that what we've got is we have x term and a y term, and basically separation of variables is just a fancy way of saying that we collect the like terms. That basically means we're going to put all of the x terms on one side and all of the y terms on the other side. So if I was to do that with this question here that I've just made up, if I put all the x terms on one side, well, I'd need to multiply both sides by dx. We treat it like a fraction, so I'd have something like x plus 6 dx equals 7y dy. Then the next step is just to put an integration sign in front of both sides, and then what we're going to do is this side over here we integrate with respect to x, so integrate with respect to x, and on this side we integrate with respect to y. So it's basically like collecting like terms. We put all the x terms on one side, integrate, put all the x terms on the other side and integrate. Now when you integrate, you know that creates a constant of integration. Now when we integrate, we're not going to put a plus c on this side and a plus c on this side. what we'll do is just we'll have 1 plus c when we integrate. So we'll stick whatever constant we would have got and put it on one side. Okay, so just use 1 constant. So you're not going to write out plus c on both sides and then cancel it out. That wouldn't make any sense. So we just put 1 plus c on one side, and then if we've got our initial conditions, then we can use that to work out c and get our particular solution. So we need to find a general solution to this differential equation here. So we start by the separation of variables, basically collecting like terms, where you put all the y terms on one side, all the x terms on the other side, and you think of dy as a y term and think of dx as an x term. So my suggestion would be, let's just write this down, 1 plus x squared dy dx equals x tan y. My suggestion would be that you multiply both sides by dx first, and then that will tell you which side to put your x terms on and which side to put your y terms on. I'll show you what I mean. So if I multiply both sides by dx, I'll have 1 plus x squared dy equals x tan y dx. Now what that's telling me, because the dx is over here, I need to get all my x terms on this side. Because the dy is over here, I need to make all the y terms go on this side. So if we do that, so if we get all the y terms over to the left, that means we're going to have 1 over tan y dy, and then if I divide both sides by 1 plus x squared, I'll have x over 1 plus x squared dx. Okay, so we've now separated out the variables. The next thing we do is we integrate both sides. So you just put an integration symbol in front of both sides like that. And we now need to decide how we're going to integrate both sides. So first of all, 1 over tan y is actually cot y. So I'll write cot y dy. And then we'll leave this side as it is for the time being and see if there's a method we can use. Now cot y or cot x is in the formula book, and in the formula book it says that if you want to integrate cot x dx, that equals natural log of the modulus of sine x plus c. So that's in the formula book. And this side, I recognize that it's this pattern, f dash of x over f of x. So then what I do is I try the log of the bottom and then make any adjustments. So that basically is telling me how I'm going to integrate that. So let's do that over here. So I will have on the left hand side natural log sine y. I don't put plus c just yet. I'm just going to put 1 plus c at the very end, equals, so first of all I'm going to try the log of 1 plus x squared. Now I differentiate it to see how good my try is. Now if I did differentiate that, that would give me 2x over 1 plus x squared. So I need to adjust it to make sure I just get x over 1 plus x squared. So I put a half here. Then I have plus c. Right, now I can leave my answer in that form. That is absolutely fine as my final answer. But the next bit, what I'm now going to do is I'm now going to attempt to make y the subject. Okay, so we can leave our working here, but I'm going to make y the subject. So I'm just going to do a few more lines of working, which is sort of optional. So this next bit here I would suggest is optional. Right, so the first thing I'm going to do is take that half. So I'm going to write log sine y, take that half and write it as a power. So I've now got log 1 plus x squared to the power half, and then I'm going to write my constant as the natural log of a different letter a. So basically what I've done is say let c equal natural log of something. It's just another way of writing a letter. Now the reason I've done that is it will allow me to put everything together, or at least what's on the right hand side. So this will become the natural log of 1 plus x squared to the power half times by a. So I'm basically using the rules of logs to put those together. That should be a modulus sign there. So this side is still log, natural log of sine y. Then I'm going to raise each side to the power e. That means that the e and the log cancel out. So that will now give me sine y equals 1 plus x squared to the power half times by a. And then I could go a step further and do the arc sine of both sides, so that y equals arc sine of 1 plus x squared to the power half times by a, and I suppose I could write the a at the front. So here we have at the very end, in this form, where we've got y equals something, but there is no reason, unless the question says that you can't leave that in that form. It doesn't specify which form it needs to leave it in, but I suppose if it says a general solution, you want to leave it in the form y equals. Right, okay. Particular solution. Now, because it says particular solution, this means that we need to find c. And the way we're going to find c is it tells us that when x is 1, y is 4, so it gives us some conditions to plug in to find c. And this one, it does say to leave our answer in this form, y equals. So let's start by writing the question out. So dy dx equals minus 3 y minus 2 over 2x plus 1 x plus 2. Right, so remember my tip, the first step is to multiply both sides by dx. So you'll have dy equals minus 3 y minus 2. Now don't be tempted to multiply out brackets at this stage, because you might have to factorize them again, so don't multiply anything out just yet. Right, so that tells me that I need to get my x terms on the right and my y terms on the left. So let's do that. Collect like terms. So if I divide both sides by, now I could divide both sides by just y minus 2, or by negative 3 y minus 2. Let's just divide by y minus 2. So then I'll have 1 over y minus 2 dy equals negative 3 over 2x plus 1 x plus 2 dx. Now I could have taken that negative 3 over as well, so then it's down here at the bottom. Yeah, it doesn't matter. If I'd done it that way, I would get an equivalent answer. Now I'm going to put the integration sign in front of both sides like this. So integrate that, integrate that. I can see that on this side here, the 1 over y minus 2, that fits this pattern. So that's the method I'm going to use to do that side, which means trying log of the bottom. On this side, I can see that this is going to be partial fractions to help me integrate that side. Right, so the left side is the easy bit to do. So if I try log of the bottom, so natural log of y minus 2, if I differentiate that to work out what I get, I do get 1 over y minus 2, so that's fine. No adjustment needed. So on the other side, let's do our working over here, and let's change this to partial fractions. So I know that I'd end up with -3 in that numerator. On the other side, I would have a over 2x minus 1, so I'd have to multiply a by x plus 2. Then I would have b over x plus 2, so that would get multiplied by 2x plus 1. So let's let x equal -2, so that would give me -3 equals b times by 2 times -2 plus 1, so that would be -3 equals, so that'd be -4 plus 1, -3b. Okay, so that would give me b equals 1. So now we will let x equal -1/2, in which case I would have -3, and then I would have a times by -1/2 plus 2. So that would give me -3 equals, that would be 3 over 2a. So that then would give me a equals -2. So that means that I would actually need to integrate, if I write it as partial fractions, as -2 over 2x plus 1 plus 1 over x plus 2 dx, so that needs integrating. So for both of those, I'm going to try log of the bottom. So log y minus 2 equals, so let's try log of 2x plus 1. So if I differentiate that, I'd get 2 over 2x plus 1. I want -2, so we just need to put a minus sign here. And then for the second one, we try log of the bottom. So I'll try log of the bottom, x plus 2. That gives me 1 over x plus 2, so no adjustment needed. So I'll put plus c. So let's write that down here. We've got a bit more space. So what we've got after integration is log of y minus 2 equals negative log 2x plus 1 plus log x plus 2 plus c. Let's simplify it so that we get it in a form that's just going to be a little bit easier, that we substitute in the 1 and 4 to find c to get that particular solution. So if I swap these around and had log of x plus 2 minus the log of that, that would be equal to the log of x plus 2 divided by 2x plus 1. So we can put those together, plus c. So now we'll say, right, at x equals 1, y equals 4. We'll substitute that in, and that will give us natural log of 4 minus 2 equals natural log of 1 plus 2 over 2 times 1 plus 1 plus c. So we should be able to work out what c is now. So we'll get natural log of 2. Don't need modular signs anymore because it's positive. If I move this across, so I'll have minus the natural log of 3 over 3. Is that right? 3 there, 2 times 1 is 2, 3, yeah. So actually this becomes the log of 1, which is 0, yeah, because you'll have 3 over 3, which is 1, and the log of 1 is 0. That's nice. So basically we're just left with that. This is what c is. C is log 2. Right, so we can substitute that in and then make y the subject. Right, so let's do that. So now we have our value of c, natural log y minus 2 equals natural log of x plus 2 over 2x plus 1 plus log 2. Yeah, so let's put that log 2 in there. So the rest of this is now making y the subject. So log y minus 2 equals natural log, the 2 can go in there, so everything multiplied by 2. So you could say 2x plus 2 or 2x plus 4 over 2x plus 1. Okay, so the value of c has gone in there, and then from there we can do raise both sides to the power of e. Let's put some work in over here. So we have y minus 2 equals 2x plus 2 over 2x plus 1, and then the last step is just adding 2 to both sides. So final answer y equals 2x plus 2, could expand the brackets if you want, over 2x plus 1 plus 2. And then I suppose if you wanted to, you could put that 2 in that fraction as well. Let's straighten out that line there. And there we go. So there's our final answer in the form that they wanted. Right, now you want to do exercise 11J on pages 324 to 326. And I would suggest probably the hardest part of these solving differential equations is probably deciding which methods you're going to use. So it might be useful just to write those down. So we've got reverse chain rule. We've got the reverse chain rule plus patterns. Reverse chain rule, we're using patterns. So that's going to be where if you see this, then you try this. And then the other pattern is if you see this. So if you see something that looks like that, then you try this. So you do it to 1 high power, n plus 1. What else have we got? We've got trig identities. We have partial fractions. We also have integration by parts. We also have as well substitution. So you've got all of these different methods. Now remember that these two here could be done by substitution, but these are quicker than changing it to a substitution. I think that covers all of the different methods that we have.